experiment to see if we can get this to work. The last talk, it was hard to see the board, so we're learning while we go along.
Well, unless she doesn't move, right? She has to stand
Right,
still.
right. So if it's a board talk, we're going to need a camera. We're going to actually need something that moves around. For these slide talks, maybe it's okay.
Oh, sure.
All right, everyone. Welcome to our first talk in the contributed session. It's my pleasure to introduce Mee Seong Im from the U.S. Naval Academy, who will tell us about universal construction, one-dimensional cobordisms with defects, and pseudo-characters.
Thank you so much for the organizers for organizing a very nice conference so far. So this is joint work with Mikhail, Khovanov, and Victor Ostrik. And the paper is on the archive. So what I'm gonna do is, because I'm not sure how much background everyone has, I'll do something much more elementary. So this is along the lines of Jonathan Brunden's first talk this morning. So let's say the cop1 sub G, cop1, comma G, this is gonna be a category of one-dimensional cobordisms where the decorations are labeled by elements of G. And here we're gonna assume that G is a group, or maybe G is a monoid. So there's associativity and identity, but not necessarily elements are invertible. So let's consider this category of oriental one-dimensional cobordisms labeled, and then with decorations by these dots, and these dots are labeled by elements of G. So in this category, the objects are oriented zero-dimensional manifolds. So because you're looking at a manifold, you have a positive orientation and a negative orientation, right? But then for the zero-dimensional guys, you also have a positive orientation. So there's really dots there, but you don't have to draw them. Like I didn't draw them. So here, the plus means this is a positive orientation, zero-dimensional guy is a point. And then the minus sign means negative orientation, positive orientation. So here, so the cobordisms look like, so those are objects and cobordisms look like this. We're reading from bottom to top. So it's a sequence of minus plus, which maps to plus, minus, minus, plus. And you're really thinking of these as concatenation of zero-dimensional objects. I'm gonna also call them by epsilon. Epsilon is equal to plus, minus, minus, plus. So in this category, what we do is that you can actually slide the dots left and right. So they can freely slide along the components of the cobordism, and then you can also combine them, merge them together like this, and then we're reading against the direction of the arrow. So when you combine this as a single dot, we're gonna read from left to right, GH. So the dots can merge.
Wait, can I ask you a question? So,
Yes.
Is this embedded or because you're drawing crossings?
Yes, well, not really embedded. These are gonna be really virtual crossings. We don't care.
Okay.
Yeah, exactly, just virtual crossings. Maybe in other contexts, which one is over each other, maybe that matters. But in this context, it doesn't really matter. Yes, good question. So now, what is the definition of a TQFT? TQFT means topological quantum field theory. For this category called 1G, and we're working over complex numbers, is a tensor symmetric monoidal functor, uppercase F, which takes which is a map between this category on the left to this finite dimensional complex vector spaces, finite dimensional representations of G. So this is a definition of a TQFT. So here, what we have is that under this functor F, it's going to map this plus sign, zero-dimensional plus guy, to finite dimensional vector space V. It's going to map the minus guy, zero-dimensional, the one with the minus orientation. It's going to map it to V prime. And then the cop and cap morphisms. So the first one on the top, we're going to call that cop. The second one is a cap. These morphisms induce these maps. When you apply the functor F to this morphism, to this cobordism psi, when you apply that, this is really a map from complex numbers, the base to V prime tensor V. And then this other guy here, this is really, when you apply the functor uppercase F to this cobordism, it's really a map from V tensor V prime, which maps to complex numbers. So this cop and cap morphisms, they induce these maps, and the isotopy relations here, these two imply that V prime is actually isomorphic to the dual of V. And V star, that's actually a map from home, from V to complex numbers, such that this psi and V are standard diagonal and in evaluation maps. What do I mean by this diagonal map? psi is gonna take 1 to the summation vi tensor v subscript I. These are the basis elements. V sub I are the basis of v, and v superscript I is a basis element, a basis of v dual. And then as for this v here, this is gonna map vi tensor vj to delta ij, the Khovanov delta. Question? Yes.
If there are no dots, is that like the unit element of the group?
Huh?
If there are no dots in the strings, is that the unit element of the group?
Yes. You could put a dot label as 1 or unit. Yes, that means it's, yeah. Correct. So to plus and minus endpoints, we're really assigning vector space and the dual vector space, respectively. The defect labeled, so this is what we have here, and a defect labeled G on an upward-oriented line. Whenever you have a defect G, this is really corresponds to multiplication on the left by element of G. So it takes a vector to add G times V. This guy here, this is really a map from V tensor V dual to complex numbers, and then it takes V tensor F to F of V, F evaluated at V. And then this other cobordism, this is the map from C complex numbers to V tensor V star tensor V, which maps 1 to this summation of the basis elements, Vi tensor Vi. So sliding along the cobord cap, it shows that dot labeled G. So now when we have this rather than plus plus, whenever you have an arrow going downward, this guy here, when you apply the functor F, this is really an M sub G dual. It's a dual of the multiplication map, what we saw before. And then when you have a circle with a dot labeled by G, this evaluates to trace of G over the representation V. And then we also write it as chi V of G. It's like a character of G over the representation V. And then, so this one's a character. We also have this conjugation invariance of characters. Because of conjugation invariance, chi of GH is equal to chi of HG. You can slide this H over in front of G, move the last letter to the front. We have this graphical interpretation by what does this mean graphically? It means that you can slide the G down around. So H is on the top and G is on the bottom. Okay. So now, contrast to TQFT, in topological theory, let's talk about topological theory, which is different from TQFT. So we're given only evaluation of closed manifold, which means it takes empty manifold to empty manifold, empty zero-dimensional guy to empty zero-dimensional guy. Those guys are called closed manifolds. So to a G-decorated circle, we assign, so basically it's a circle with an orientation, a dot labeled by G. We're gonna assign the number F of G, which is a complex number. Isotopy property, here, this is the isotopy property, right? F of GH is equal to F of HG. This isotopy property basically implies that F is a function of conjugacy classes. O sub G is constant of conjugacy classes. So given such an F, lowercase f, you can build this notion called state space. Think of these as like a vector space. State space for oriented zero-dimensional manifolds, epsilon. So these epsilon is assigned sequences, pluses and minuses, by looking at all the closed G-decorated one manifolds, Mi, which bound epsilon and the unimpulses relation that this summation, linear combination is equal to 0 if and only if, no matter how you close it up, with any other cobordism, whose boundary of M is also equal to epsilon, you're taking this notion of this duality here. And then you evaluate using F, this is going to evaluate to 0. I'm going to explain that graphically on the next slide in more detail. Yes? The bracket?
Your closed manifolds, do you only have the circle, or do you have anything else?
Circles.
So only circles, right?
Circles. One dimensional, the closed guys, you have spheres, right? If you go up by one dimension, it's like a sequences of circles to mapping to tensor products of circles. You have all these pairs of pens with genuses, right? Putting holes. These guys, the closed guys, are just circles in this context.
I thought that you only had circles because all your crossings are virtual. So it's not you can undo them, but maybe at times.
When you have a circle and maybe another circle that's crossing each other, you can put them apart. They're virtual crossings, so they're just, it doesn't really matter. But you do have two irreducible components, if that's what you mean. Two closed irreducible components. Yeah. So now, so if boundary of M is equal to epsilon, the sequence epsilon has it has equal number of pluses and minuses, and that's called balanced sequence. In particular, a state space is equal to 0 if and only if the number of pluses does not equal to the number of minuses. In this context, in that case, that's called unbalanced. Here's an example, plus minus. So manifold M with a plus minus. So this is an example here. This is a G labeled arc, and the linear combination of this guy. Here's a linear combination graphically. Summation of lambda I and this guy is equal to 0 if and only if, no matter how you close it up, no matter what you have for M, whose boundary is also plus or minus, it must be the same. So before we saw M bar, right? So M bar basically means you fix the horizontal line, you pick up this arc, flip it to the other side, so you have an arc moving to the left. So you have a cap moving to the left. But the bar means reverse the orientation, so you're actually moving to the right. So you get a closed guy, closed one-dimensional manifold. So no matter how you close it up, like this, is equal to 0 for all G and G. This relation. So for longer balanced sequences such as pluses and minuses, plus, minus, minus, plus, plus, minus, there are k factorial ways to pair out the pluses and minuses, right? And then we can decorate the arcs by elements of G, giving more complicated state spaces. You can come up with much more complicated state spaces. Now, what is a cobordism? When you saw a cobordism from epsilon prime to epsilon, induces a map of state spaces. So if cobordism means you have epsilon prime pluses and minuses on the bottom, epsilon pluses and minuses along the top, and you have a cobordism from epsilon prime to epsilon. And what we're doing is, you take something from A of epsilon prime, from this state space, you're looking at this cobordism, and then you compose that with M. So this guy here, M composed with M prime. The boundary of this, boundary of the composition is actually equal to epsilon. So this is how we compose. We just stack them on the top. They fit together to give us a functor, A sub F, which is a cob1G, which maps to finite dimensional complex vector spaces. And then remember that lowercase f, we're always gonna, throughout the whole talk, f is gonna be a function that's constant on conjugacy classes. This condition here, this is just called lax TQFT in the sense that we have this tensor product of state space, tensor product with this another state space. This is always an inclusion because you have these arcs on this left-hand side, you have arcs on the right-hand side, but they cannot cross over, but you have all those arcs on this other side. So this guy's bigger. So there's always an inclusion, and that's called lax TQFT. We want to know when do we have an isomorphism. And that's when we have a true TQFT in a TS sense. So here for TQFTF, this is what we really have. F of epsilon, epsilon prime is isomorphic to the state space F of epsilon, tensor F of epsilon prime. That's what it means for any epsilon and epsilon prime. So we said a topological theory lifts to a TQFT if they're a map of state spaces. So this guy here is lax TQFT, this guy here is TQFT, such that we have this intertwining map, gamma of epsilon, over all morphisms. In particular, gamma respects evaluation of closed morphisms, G-decorated circles. So our main question is, given the topological theory AF, when does it lift into some TQFT? When do you get a true TQFT? What are the conditions? So this can be, so what you can do is you can always study this with different categories, not always the category that we're talking about today. Other categories of decorated cobordisms and higher dimensional ones too. And then you'll see that there are going to be obstructions to the lifting. So in our case, the category of cobordisms is cob1G. So basically, if a topological theory AF associated to the function f, you can lift lowercase f to a TQFT uppercase f by a representation V. Then a circle with like a no defect, or maybe a defect labeled by 1, is gonna evaluate the dimension of V. So we see that there's an obstruction. There's no lifting if f of 1 is a strictly complex number minus the natural number. That's not a natural number. So here's an example. Suppose G is finite. Any complex valued function f on conjugacy classes is a unique C linear combination of characters of irreducible representations of VI. So as long as f is a function that's constant on conjugacy classes. It's going to be of this form, summation of lambda I chi I. Lifting to TQFT exists if and only if this function here is a character, which means this lambda I, the coefficient must actually be a natural number, 0, 1, 2, must be positive, must be a non-negative integer for all I. Then you actually get this V, which is a direct sum decomposition. V is equal to summation Vi lambda I, which gives us a TQFT, lifting the function lowercase f.
Sorry, so are the VIs associated with the characters then?
Can you?
Are the VIs associated with the characters then?
Yes, yes. This VI is right?
Oh, yeah, so those are just irreducible representations.
Yes, irreducible representations of these VIs. Yes. Yeah. Okay, so in number theory case, now you assume that, let's assume G is arbitrary. It turns out the lifting property has been studied by people, a lot of mathematicians in number theory. Andrew Wiles, Taylor, Mikhail, Mee Seong Im, Chenevier, and then what they do is that in all these papers, they're studying like given any function f, lowercase f, which is constant on conjugacy classes, when you lift it to a true like representation, TQFT. We're going from pseudo representation to a representation. But then they never mention anything about TQFT or topological theory, no geometry, no topology. So also they're also interested in when G is a Galois group. But then the results hold for any G, group G, or a monoid G. And then basically you start with a function on G and you want to prove that it's a character of a representation. And often it's a Galois representation. Function f on G takes values in more general field or local rings. But then in our talk today, we'll work over complex numbers. Okay, so now what are additional properties? These are this conjugacy invariance. For it to be a character of a representation, what other properties do we need? So now let's look at this. Wedge and V, this is the exterior power of V, which is a self-representation of V tensor N. And then here we have this first map is P surjection together with inclusion. So when you do inclusion followed by projection, you have this identity on the exterior product of V. This is called an idempotent. Idempotent is you apply P first and apply injection. This is a projection onto wedge and V. And then we also call this anti-symmetrizer, full anti-symmetrizer. This is a sum over all permutations, sigma in Sn. Key observation is that whenever n is greater than d, d is equal to the dimension of v, then whenever you take wedge and v, this is always going to be equal to 0. So in particular, the composition, this anti-symmetrizer, full anti-symmetrizer, En minus, you compose that with H. H is going to be any linear operator in V tensor N. That's also going to be equal to 0, right? As long as N is greater than D. And then when you take the trace, it's still going to be equal to 0. So for a linear operator, what we're going to do is we're going to choose the product of multiplications by GI, the operators, like the H is going to be of this form. M left multiplication by G1, right? Tensor left multiplication by G2, MG2 up to MGN. And then whenever you have any permutation, it's going to be swallowed by this full anti-symmetrizer. What do I mean by that? You apply tau, x on En minus. That's just going to be equal to, En minus is you're doing a sum over every element in Sn. So this is going to be equal to, you're just permuting the strings. So that's equal to some sign, -1 to the length of tau times this full anti-symmetrizer. So what we can do is we can keep the connecting lines straight. In the next slide, we do have a picture, diagrammatic that goes with this. So now if you want to relate this to topological theory and TQFT, we're going to convert this to this graphical notion. So whenever you have a box labeled by n and strings going up, strings going down, like strings are all moving upward. It's always defined to be this guy. 1 over n factorial times summation -1 to the length of sigma times the sigma. Sigma is an element of Sn. This is the full anti-symmetrizer. And then whenever we close this up, you can decorate each one by elements of G, G1, G2 up to GD plus 1. Whenever you close this up, the closure of this guy is equal to 0, no matter what G1, G2, GD plus 1 you label it. And then the closure of, you take D strings, take one of them out. Whenever you take D strings and close it up, it's not equal to 0 for some combination, G1 up to GD. So this is a pseudo-character equation. Yes?
Are you assuming that this happens? Is this?
No, this is a definition.
Oh,
This
okay.
does happen, yeah. Yeah, this is what it means to be pseudo-character. And then the algebraic definition is also given here. Algebraically, the pseudo-character equation, we can write it as this full anti-symmetrizer, right? E d plus 1 minus. And then you compose that with G1, G2, up to G d plus 1. These defects on the top, and then you close it up. That's what it means to take the trace. You close it up. It's equal to 0 no matter what combinations of G1 up to Gd plus 1 we decorate, no matter how we decorate this. So here's the definition. A conjugation invariant function is called pseudo-character of degree D if any G1 up to Gd plus 1 closure of the D plus 1 anti-symmetrizer evaluates to 0 by F. And then some closure of D anti-symmetrizer does not. So most functions, so here are some facts. Most functions that's constant on conjugacy classes, they are not pseudo-characters of any degree. A character of a representation of dimension D is a pseudo-character of degree D. And a pseudo-character F of degree D satisfies F of 1 will be mapped to D. So we mimic the equation where chi of 1, the character of 1 is just equal to dimension of V. So let's do an example. Degree 1, D is equal to 1, pseudo-character. So suppose F is a pseudo-character of degree 1, so there is some G. You can label this closed diagram by some element G. That's not equal to 0. So this is this guy here. This is the anti-symmetrizer, right? And then you compose that with some H. What we do is we clear the denominator. That's why we have this 2 on the front. N factorial is, or D factorial is actually in the front. So this guy, whenever you see a box, you just delete it, erase it, and replace it with the identity element in Sn, and then minus the, the transposition 1, 2 here. And this is equal to 0 because this is a degree 1 pseudo-character. So now, what do we mean? This means that f of g1 times f of g2 minus f of, we follow along the string. You can untangle this, right? Just pull this out. So f of g1, g2, that's the second term here, that's equal to 0. So what this means is that you can move this to the other side. Move this to the other side, but then flip them, you get this guy. F of g1, g2 is equal to f of g1 times f of g2 for all g1, g2. And then because there exists some g where f of g is not equal to 0, we have f of g1 equals f of g times f of 1 by this condition up here. So this tells us this is equal to f of g, right? So we have f of 1 goes to 1. So f is a homomorphism, map from G to C star. So in this case, for this degree 1 pseudo-character, we get a one-dimensional representation of G. This is a one-dimensional representation, C times V, where G acting on V is just as F evaluated at the same G times V. So any degree 1 pseudo-character is a character of one-dimensional representation, G. Yes,
Did you use like a scaling relation to?
Scaling relation?
Yeah, did you compose this?
Oh, no, you mean here?
Yeah.
No, we're just applying the full anti-symmetrizer. That's what the box means together with the strings. Do I have okay. So for any group G, if F is a pseudo-character of degree D, then F is a character of a representation of G, of dimension D. So Taylor and other, his colleagues and other mathematicians, they generalize to other fields. In the case when D, so if we're going to work over prime characteristic, that's also interesting, and that's a paper, SQL paper that we thought about a little bit, and that's something that we would like to write. Or if you'd like to collaborate, we would like to bring in more people. But case when D factorial is not invertible, like in the ground ring is more complicated. In that case, the idempotent EK minus projection onto wedge KB, this is not available. This doesn't exist. So you cannot divide by K factorial. So this should correspond to diagramics. If you want to work on this over other characteristic, where what we're going to do is we need to introduce lines of thickness K up to D to mimic traces of G on exterior powers of V. So this is a work in progress or open problem, another characteristic. And even other fields is an open problem, like Galois. So I think I have about 1 minute. So what I'm gonna do, this slide is about higher dimension. N actually means, rather than using like looking at two-dimensional cobordism, which means the boundaries are one-dimensional circles, and then the morphisms are one-dimensional, right? Two-dimensional surfaces. This is the case of n-dimensional guys. So the cobordisms between n minus one-dimensional manifolds, you must satisfy this multiplicative condition. And then whenever you have no boundary to a no boundary, it's gonna take that object, you should evaluate to 1. This is a definition of pseudo-character for higher dimensional case. This is also a work in progress, or it's an open problem for higher dimensional setting. And I think, so I should say this is by Mikhail Khovanov and Radmila Skandovic. She's a faculty member here. She's a professor here. So they came up with this theorem. State spaces for f are finite dimensional if and only if this generating function is a rational function. So this rational function, this rationality implies the surface of higher genus with one boundary component is a linear combination of surfaces of lower genus, linear combination of these guys. And this leads us to a couple of our main theorems. I'll just state one of them. A function f is this function that we've seen earlier in the talk. This is a pseudo-character for COP2 if and only if it's a character. It's coming from two-dimensional TQFT, so it goes about both ways. And then I'll stop here. Thank you for your time.
Any questions for our speaker?
Do you have example of like a pseudo-character of degree 1 for COP1?
For COP1,
Yeah.
do I have an example?
Yeah. Or do you know? You said degree 1 is character, basically.
Yes. So the character. So this is true for COP1 and COP2, but then not for higher, more general setting. Like the pseudo-character, if and only we have a character. F is a pseudo-character. If and
So
only
pseudo-character of degree 1 for COP1 is again a character.
Yes.
I see.
Well, I think there's some conditions, but
Okay.
In the
yes.
statement of this theorem, there's no defects. Is that right?
Oh, there's no defects, right. Because you have a lot of choices for defects. You could put one-dimensional guys, codimension 1 or codimension 2. Codimension 2 guys sitting on one-dimensional guys. So the defects, the dots, they're actually sub-manifolds. So the notion is coming from physics. Why are they called defects? So they're actually manifolds that's embedded in these cobordisms, like these surfaces, or the strings.
Do you have this? Oh, sorry.
Oh yeah.
So sorry. Do you have a statement? Do you expect a statement like this to be true for defect?
Oh, the one
TQFTs?
with defects? There should be some conditions. If it's not true, if and only if. If it's not true, then we just need to impose some more conditions, just like what we have. But all the theory, the idea is coming from number theory. Everything is driven by number theory. So we were digging up a lot of papers from 30 years ago, 40 years ago, and then so we're making a lot of connections from multiple fields, and then we're writing more papers in the number theory direction. So there's a huge, rich area that a lot of people in geometry, rep theory, topology that they haven't discovered or they haven't made the connections yet. Yes. Yeah.
I can ask later.
Okay.
I'm sure we'll-
Okay.
Any further questions? Okay. Join me in thanking our speaker again.